Yes, welcome everybody. Today I will give a presentation about Mailman, a Clojure event-driven library, as the title here says. I am Wout Neirynck. We already talked a little bit about how I ended up using Clojure. So a little bit more about me. So I'm Wout Neirynck. I'm living in Belgium. I have 2 kids. I've studied at Ghent University. I have a master's degree in software development, and I've been writing software professionally since 1999. Some other things you need to know about me: I'm a big fan of test-driven development. To paraphrase Winston Churchill, it's the worst form of software development, except for all the other ways we've ever tried. In my opinion. I also am a privacy advocate. I think that privacy is much more important than many people realize. Recently I've founded Monkey Projects, and I've been building a new tool, a Clojure-based CI/CD pipeline called Monkey CI. There is a link, or there will be a link at the end of this presentation for those who are interested in it. So the agenda for today, first of all, I will explain a little bit the high-level view of what Mailman actually is. I will elaborate a bit on my design decisions. Then I will also explain the various concepts that are used in Mailman, because that will make it easier to understand some of the code examples, and especially the live coding session at the end. Also, you will then see some of the functionality it provides. I will also talk as a test-driven fan on how to use Mailman in your tests, or how to write tests around it, how to test your code that is using Mailman. I will also elaborate a bit on the various implementations. What that is will become clear. So then there is a short live coding session where I will be showing a little bit of the Mailman, how to use it in real life, and then afterwards there will be still time for some questions. So what is Mailman? A Clojure library, event-driven. We already discussed it, so I'm assuming that you all know what event-driven is, but to be certain that we're on the same page, to me, event-driven is an application where the flow of the application is driven forward by events. So no requests, HTTP requests or things like that, but they are asynchronous events. So it's not possible to just reply to requests. That the flow happens in another way. And I developed it because in the course of building Monkey CI, which is also as a CI/CD tool, very event heavy, I encountered lots of problems trying to write my code with these events, in a maintainable fashion, testable, how to handle side effects, things like that. I didn't find any existing libraries for that. There are, of course, many things regarding HTTP where you can, that is a very established domain, but for events, it was a little bit difficult. So I decided to write something myself. And so these design decisions here are a part of that process. So first of all, as I already said, it has to be very testable. I think that is something that many libraries are lacking. They live a little bit on their own island. They don't think about how to use this in a test-driven code base. So I wanted to make sure that Mailman really made that possible. I also, because of most applications that are HTTP request driven, there is a lot of code there, and a lot of good understanding of the development community on how that works. So I wanted to have the same feel with that, so I wanted a little bit the same. So it's like you would be writing an HTTP application, but with events instead. How that goes, you will see. Also, of course, very obviously, it has to be independent of the underlying message broker, the structures. So you needed to. Myself, I already used it on 3 different platforms, so it was even a requirement for myself. And it has to be very flexible. What do I mean by that? I don't like libraries that impose a certain way of working on the developer, and I think that Clojure is actually a good platform for that, because it's a little bit ingrained, it's a bit in the Clojure DNA to be flexible. Clojure libraries are very often more like a toolbox where you can use the things that you like and not use the stuff that you don't need. But there's no data hiding or encapsulation, something that you have a lot with OOP, Java, for instance. Everything is so hidden that it becomes very difficult to extract a little part of it. So I didn't want that. It had to be flexible. So those are the ideas behind the library. So concepts here. I will sum them up briefly here, and then I will explain each of them in the slides after this one. I limited them to 7 because I once read that when giving a presentation, people have a hard time grasping more than 7 concepts at once. So here they are, 7 things. So the event posters, event receivers, the listeners, routing and handlers, interceptors, the context, and then the brokers. So first of all, the event poster. I think this one speaks for itself. It's simply a protocol where that has a single function, post events. So an events are posted to the broker, to the underlying system, sent out, and hopefully somewhere someone will receive that event and do something with it, or multiple components. I deliberately also made it so that you can send multiple events at once, because some implementations provide ways to do batching, which makes it more efficient, and I wanted to allow implementations to make use of that. Now its counterpart, the event receiver. How do you get events? This one has also a protocol, and it has 2 functions. So the one way to get events is to poll explicitly for them. In this case, I have provided a function that allows you to ask for up to any number of pending events, or if you specify nil, then it will give you all events that are pending. Or the other way, perhaps more used, is to register a listener, add listener, and to the broker, to the event receiver object. This listener is then also a thing that gets notified whenever an event is received, and that thing here is also protocol. Typically, a listener at least should have a handler function. That's just a plain Clojure function that has 1 argument, the event that is incoming. But the listener here, as you see, is a little bit more complicated than that. So there's indeed the invoke function, which the responsibility is to actually pass the event to that handler. How that goes, you will see later in some of the examples. But there's also an additional function that I added to unregister. This may be useful if, for instance, you want to do a clean shutdown, or sometimes maybe you have temporary listeners that you only need for a short period of time. This function allows you to unregister them after you have registered it. And in this case, it returns true if it got unregistered and false otherwise. It's nice to have. Also an important feature here, or an important concept that is not in the code comments here, is that the handler, if it returns a value, that value is interpreted by Mailman as new events that will be sent out again. So I have this idea of an event-driven application as independent modules that receive events but also generate or can generate new events. And I didn't want to sprinkle all post-event calls all over my code. That was one of the problems I had in the beginning. So that's how I solve it in Mailman. It's the return value of the handler that say, okay, I have processed an event and I have new events that I want to send out. So that was one major part of Mailman. It's the whole abstraction a little bit of how to send and process events. It could end there, so you couldn't just create a listener, pass it with a handler function that does what you want. But large parts similar to an HTTP library where you have your handler that can just handle any request. Typically, you want some form of routing where you say, okay, this request needs to go there, this request needs to go there. The same with events. This type of event needs to go to that handler, this type to another handler, things like that. And that's where this routing comes in. So this decides which event based on several parameters, which I will elaborate on, are going to which functions. And for that, there is in the core of Mailman a make router function. So this function here, you can see it a little bit in a very simple, very basic example in action. So this code sample here shows two event handlers. They don't do anything, they just print something. And below that, you see the routing structure. So this actually declares how events should be handled, should be processed. And in this case, they are just a list of pairs. And the first is, in this case, the type of event. How that goes will become clear. And the second part is a list of handlers. So minimally, a handler, as you see here, is a map with a handler function that will receive the incoming event. You can have more than one handler. They are invoked one after the other or in parallel, depending on how they are dispatched. And at the bottom there, you can see also how the router is created. In this case, it's just the most basic call to the make router function with the routing structure. Now, this make router function also accepts an optional second argument, which is a map of options. And you can see here on the left side the three possible options that you can pass to that make router function. So you can specify your own matcher, you specify your own dispatcher, and possibly also an additional list of interceptors. There are sensible defaults provided, which I will elaborate on now. So these three possible options. So in the example, you saw that I specify an event type. That's not imposed on you. So again, the flexibility, you can do what you want. In my case, I tend to always have a type in my events, and that type is used as the property that will decide, okay, which handler needs to be given this specific event. So the default implementation, if you do not provide your own matcher, will just take the type out of the event and look it up into that routing structure and say, okay, this type can be handled by these matchers. If nobody can handle the event, then it is silently dropped. The second possible option is the invoker. So once you have your list of handlers, how should they be called? The default is one after the other. So if you have 5 handlers for a single event, first one, then a second, and so on. An alternative implementation, which is also provided in Mailman, by the way, is doing them in parallel. So then it starts any number of threads and calls them in parallel. But in my case, I've always used the synchronous way. Besides, in practice, you will hardly never have more than one handler for a single event type, but it's perfectly possible. Then also as an additional option, you can also specify interceptors. So the interceptors, how that works, I will explain later, but it's possible to specify interceptors on the level of each handler, but also global interceptors, which are applied on each and every handler in the entire structure. It could be useful for, I think, security checks or validation or logging, things like that. Now, to elaborate a little bit on the matcher, so one of the 3 options I previously explained, it's also a protocol, not just a simple function. Why is that? Well, first of all, there are 2 functions in the protocol. The most important one is the one that allows you to actually find the handler. So you see here, it's the second function in the protocol. It receives the routing structure and the event that is being processed, and it's up to this function to decide, okay, which list of handlers should be given the event. So this function should return a list of handlers. But since that is not always the most optimal way, there is also a compile function provided. So it allows the matcher to rearrange the structure of the routes in a format that is more suitable for its needs. So below that, you see the type matcher record. That's the default implementation I mentioned previously. So if you do not specify a matcher, that's the one that you will that it will use. So what this does is it just compiles the routes by putting them simply in a map, which makes it a lot faster to look them up, and it matches by type. So we see here the last line of the example of the snippet here. It takes the type from the event and then looks that up into the compiled routes. So the routes that it receives are actually the compiled ones. In my case, I've only ever needed that one, but I can imagine especially if you're using this, or if you would be using this in a larger system where you don't have control over the format of the events, that maybe, I don't know, there's a header with that determines which type it is, or I don't know. This here you can override that behavior. Now, interceptors have previously been mentioned. I think interceptors are a fairly well-known concept in the Clojure world, and maybe also in functional development in general. Especially the HTTP libraries make heavily use of it, or they use middleware, but it's more or less the same concept. So you have, how it works is you have a context map, and your interceptors have 2 functions, an enter and a leave, or one of the 2 is also possible. And the interceptors are chained. So there's a chain of interceptors, and when you execute it, is how it's called. You enter the context. How that context looks will also become clear. Each interceptor has a possibility on its interface to manipulate that context. The last interceptor is the actual event handler. So in Mailman, the event handler, which is originally just a function, is also wrapped in an interceptor, and the result there is also added to the context, and then it's again passed up the chain using the leaf functions. Now, I did not write that myself. Implementations already exist. I chose the one from Pedestal because Pedestal is a well-known library. It's already battle tested. It has a lot of functionality. It's well documented. So I will not go into too much detail on how interceptors work here. If you want to know more, I propose that you look into the Pedestal documentation. It also has functions for error handling and things like that. So let's look at some examples of interceptors. Mailman provides some fairly high-level utility interceptors. They are located in the monkey.mailman.interceptors namespace. This is one of them. What it does is just tracing. So the interceptor has a name which ideally should be unique in the chain, and it has both an enter and a leave function, and on both ways in both functions it just prints out the log and returns the context unchanged. So you see the context at least contains the event, so that's a key that is always present in the context in Mailman, and the leave here prints out the result. So this get result, the last argument of the trace there, is actually the return value of the event handler. So I already mentioned that one of the ideas behind Mailman is that this return value is used or is interpreted as events that should be sent back out. So this here is a way to see that. Interceptors can even manipulate that result, can do things with it. That's also possible, can even remove it. Everything's possible with interceptors. That makes them so powerful. Now this here is the handler. I already mentioned that handler, which is just a function that accepts the context as a single argument, is internally wrapped in an interceptor, and this is the code for that. So what it does is it just calls the handler with the context, puts the response, the result, the return value in the result key, and it also adds the handler itself to the context. Could be useful for debugging purposes or I don't know, logging, things like that, inspection. So this context has been mentioned several times now. This is a contrived example of a context. So I already mentioned that by default, it always contains the event itself. But interceptors can manipulate it. So in this example, several other interceptors have added some values. Typically, why do you use interceptors? Probably because you want to do some kind of side effect, or because you have a repeating thing that you want to reuse elsewhere, and this makes it possible. Typically, or maybe perhaps you could, I don't know, start on the enter start database transaction, on the leave commit it. That's a possible example, or I don't know, add HTTP client that others can use, things like that. In this example, you also see that the result is also in the context. As I said, the result is interpreted as a list of events. In this case, you have a single event that is supposed to be sent back out. Now, the last of the concepts here is the broker. The broker is actually just a combination, or typically a combination of implementations for the event poster and the event receiver. Usually they will be combined into one thing, a type or a record or something, or a class. But in specific cases, I guess it's very much possible that only one is present. I can think of situations where modules will only need to receive events and never will need to send them out, and it's possible you have a receiver only and no poster, but typically they will occur both. So the broker is actually, it's a thin layer on top of an existing implementation, something else that's below that does the actual event management. So the current implementations I have already written for Mailman as one for JMS, which is more or less the Java standard for messaging and eventing. Nuts, which is perhaps not that well known, but it's an implementation, a messaging implementation that tries to create the best of both worlds, or combine the features of the JMS style and the Kafka style. So they have regular messaging JMS style, but there's also a layer that allows for persistence, message replays, and things like that. I've been using it for some time now, and I think it's really powerful. I also added an implementation for Manifold. For those who do not know what Manifold is an in-memory, as an asynchronous library in Clojure, more or less similar to Core Async, although it represents itself as more of an abstraction layer over other async libraries. I like using it, and I've also added an implementation. This could be useful if you only want to use Mailman in an application that does not communicate with other tools. So to do eventing inside your process, that makes it very useful there. And I've also added an in-memory implementation, which is in the Mailman core library, simply for testing. It uses Java queues for testing, but it's more or less similar to the Manifold one, which is also in memory, but Manifold is, I think, more powerful. So each of these implementations are located in their own libraries. So the core is a library, and then there's a JMS library, a NUTS library, a Manifold library. The in-memory one is actually in the core, so that you don't need an additional other dependency for that. But they are all in the same GitHub repository, so it's a monorepo of multiple libraries. And maybe in the future, I will add the Kafka implementation. I know Kafka is one of the most well-known and popular event platforms. I've used it myself for quite some time. I know a lot of it. But yeah, since I have not needed it right now, or up till now, I have not written an implementation. But yeah, who knows? Maybe I will do it, or maybe someone else will need it and will create a pull request or will write a library of their own, which would be very, very nice. So all that information, I'm putting it here in a single picture, because the picture says more than 1,000 words, they say. So this is the flow of an event throughout a Mailman. So step one, the broker receives an event, passes it to the listeners. Depending on the implementation of the broker or how the subsystem goes, this will be sent to all listeners or to only some listeners. I will explain more on that on the implementation, JMS implementation slide. So then the listeners send that to the router, which is encapsulated in the listener, and then the router there, with the matching mechanism I explained previously, will look up any possible handlers, which in turn are interceptor chains. So the whole interceptor chain thing that you see there on the right is actually a pedestal code. So a Mailman executes the interceptor chain using a pedestal. Then, if there is a result in the context, this result will be used to send out new events using the event poster. And in turn, that will send it back to the broker for actual sending over the network, I assume. Now testing. So I already said that testing is an important part. It's something that I think is often neglected, which it shouldn't. So there's this kind of code can be tested on several levels. First of all, you can just unit test your handlers and interceptors. So handlers are usually side effect free, usually pure functions, which should be fairly simple. Interceptors can be or can have side effects, which makes it maybe a little bit more challenging. But again, they are just functions. An interceptor is a structure that has an enter and a leave function, so it's fairly possible to treat that as regular functions that need to be tested. So I will not go into detail here in this presentation on how to do that. Something else that I think is the most important part here is how to test your routers. So we already saw the routing structure. These were just simple ones, but in a real application that can become a very complicated structure with many types of events, with many handlers. Each of those handlers can have their own interceptor chains. So it's very necessary to be able to test that. Now, of course, the problem here is that these interceptors often, as I already said multiple times, can have side effects. So yeah, how do you test that? Well, Mailman offers a solution for that, and I will show you in the code examples how to do that. And then there's a third layer, which is actually the top layer, broker test in itself. So we can connect to your broker, send out messages and things like that, but those are, in my view, are actually integration tests or end-to-end tests, and that's a whole other category of issues. In Mailman, I think the best way here is to use the in-memory broker and test it like that, but to be honest, I almost have never needed it. I just test my routers. What you can do on broker level is perhaps test serialization, deserialization, things like that. But again, that's up to you, and I will not go into detail here. It will it's a bit beyond scope of this talk. So there are, I already mentioned the various implementations. I will discuss a little bit the JMS implementation here because I think it's a nice example of how I approached the difficulties of trying to make it independent of underlying systems. So we already saw that you can post events, you can register a listener, but usually real systems, real messaging systems are more complicated than that because they want to know if you post a message, okay, where will you post it? They have an idea of topics or subjects or queues or destinations. I don't know how you call them, but they categorize their events, and you need to tell them, okay, where does that event need to go? Similarly, if you want to receive events, you also have to tell the broker from which destination do you want to receive these events. So the implementation that I made here is connecting to a JMS broker. I often use Artemis, but it could be ActiveMQ or something else. It can even be Kafka. And I'm using for that my own Monkey JMS library. Originally, I used Bowerick, which is also, I think, an often used and well-known JMS implementation in Clojure. But yeah, I needed some things that were not in there, and on the other hand, it contained a lot of stuff that I did not need, and in the last release version, they were dependent on a snapshot of something else, and I said, you know, I just write something myself because it was not that hard. It's just a thin layer on top of GMS3 implementation in Java. So I already mentioned the problem with the destination. So how am I approaching it in this JMS implementation library? the easiest way is to just allow you to specify a single destination when you create the broker. When you instantiate the broker, say, okay, this is the destination. So that means whenever you send out an event or register a list, it will always use that destination. But that's not very practical. In real life situations, you almost never have only one destination. So in practice, you need a more flexible solution, and that's why I also added a mapper function. So when you create a GMS broker in Mailman, you can specify next to the other connection settings and credentials and things like that. You can also specify a function, the destination mapper. This destination mapper is called for each outgoing event. So whenever a message is posted or an event is posted to the broker, it will pass that event to the destination mapper. And that will return, or should return, the name of the topic or queue where the event should be sent. Similarly, if you register a listener using the add listener function, next to the handler, you can also specify the destination where it should listen on. That can, of course, only be one. So in GMS speak, it will create a consumer for that topic or queue in that case. And then, of course, there is the final problem of the serialization, the codecs. How do you convert your Clojure structure to something that can be sent over the wire or vice versa? If something arrives, how do we change it into a Clojure structure? In my case, I'm only using communicating Clojure to Clojure modules, so I'm using Eden. That's the default in Mailman. So Eden is serialized to string, then that's put into a text message, which is then sent out, or the reverse, the text contents of a message is read out and it's parsed from Eden. It's perfectly possible, again, the flexibility to specify your own serializer or deserializer, again, as a constructor option. You can do that. Obviously, JSON is one of the more solutions that comes to mind, but you can use anything in that situation. Now, I already talked about the live coding, so that's what I will be doing here now. So I hope it will make a lot of the examples clear that I mentioned. So I prepared several code examples here. This is the yes, this is the. Oh, I'm out of picture. This is the example that you saw previously in the slides, in one of the slides. So it's just two simple handlers that don't do much, and the root structure, and at the end the router. So let's just look at that router. You see here, it's a structure, but it also is callable. So that's why you can pass the router to the listener as a handler, because the listener will call it as a function. So let's define an event to see how it works and put in a type evt/first I'm using here, and pass it to the router. What we see here is very simple. Indeed, the router interprets or checks the type of the event, finds the first handler, calls it, and indeed that's why you see the printout here, and also returns the context for each of the handlers. So you see it's a list of structures because the handlers themselves are also lists. You can have multiple handlers, so the response is also a list. In this case, since the handler returned nil, the result is also nil. And you saw in the code snippet of the interceptor there that it adds the handler to the context, and you also can see it here. And as I said, the event is also in the context. So that's of course a very basic example. Let's go to something more complicated. This has an interceptor example. In this case, it's of course a very contrived example. An interceptor that adds the time to the context, the current time to the context. Again, several handlers. There's 3 in this case. The first one returns a new event, and the other 2 just print out the message. And now if we go look at the routing structure here, we see, it's not large enough. There, that's better. We see that the first event is handled by 2 handlers. So this is the first one, the first handler. And indeed, it has a single interceptor. So this interceptor is applied only to that first one, not to any other one. And then there's 2 other handlers, one for the first event type, another one for the second. Again, the router is created. Let's call it here. Again, create an event. And pass it to the router. So as you see, both of the handlers are called. And the return value now is a sequence of 2 structures, the 2 contexts, one for each handler. And in the first one, you see also that the interceptor indeed has been applied. It has added the current time to the structure and also the result, which is the return value of that handler. Now let's see what happens if we actually pass this to the broker. So here, the last part here of the code, you see that I have declared a memory broker, added a listener there with the router as the handler, and I will now post that event to the broker. See what happens, and now you see again the 2 handlers are called, but the third one as well. Why is that? Because, as I said, the return value of the handler is actually a new event, and that event is now also processed by that broker. So the event, the return value is interpreted as an event. It's again posted back to the broker, which again processed it and found a new function, a new handler in the router for that EVT/second event type. This is indeed the one that is returned by the first handler. Okay, so now let's talk a little bit about testing. I already said that I would explain it in the example. So this is one of those cases. So suppose that this interceptor, there is an interceptor and it has the time, but let's assume for sake of argument that it does some very expensive and slow call to a remote NTP server, which may take up to a second. So you don't want to do that in your tests because they would be very slow. So I've also added, by the way, some functions to manipulate the context here. I think that's a little bit cleaner than just setting or associating keys to the maps everywhere. There's only a single handler for this example, which just indeed extracts the time from the context, the time that is added by the previous interceptor, and returns a new event with the time in the event. So what we want to test now here is if we invoke that router with that event is actually the time added to the outgoing event. And in this case, I'm also testing if there is the event type is of the correct type. But I do not want to call that original interceptor, the slow one. So what I'm doing here, and you can see it here, is I create or define a new fake time interceptor that does not do the expensive call, but just puts an arbitrary value in the context, and then I replace it. So the important thing to see here is that it uses the exact same name for the interceptor, and then I call replace interceptors on it. So that's a core function. Replace interceptors takes the original router and the list of interceptors that you want to replace, and it looks up for each of those handlers, looks up the interceptors with the same name, replaces them with the one you specify here, and returns a new router. This R here is actually a new router with the same handlers, and everything's the same except for these interceptors that have been replaced. That's the major reason why I did not use a regular function for the router. I did not wrap it in a function, because then it would make it impossible here to do things like that. And now if we run the tests, we see on the bottom here that they succeed, and they're also very fast. If I would not do this, let's test this one, the last one, and call the original router here. Run it. First of all, it takes some time. Second of all, it fails because, of course, this expects 100, and it did not use 100. It used the actual time. So this is how you can test your routes with interceptors and still avoid doing all the side effects. Now, as a last example code, I will show you how the JMS works in practice. So again, let's switch to the namespace. There's a single handler, just prints out the incoming event and also returns a new message. So for this example, I'm using very simple handlers. A router with a single handler here, again routers, but I now declare two topics, London Clojurians.in, London.Clojurians.out. In the background now I am running an Artemis instance in a container, and if I go down, you can see here my connection settings that I will be using, localhost, some very secret credentials, and then also the destination mapper that I already talked about. So this destination mapper here is responsible to, as previously explained, decide, okay, this event, where should it go? Which is the destination that it should go to? So let's declare a new event here. Type, what was it? evt/in, add a message, that message. Oops. And let's see if I invoke this mapper with the event, what it says. Indeed, it says that that event should be sent to the London.Clojurians.in. So this here is how it's defined. The destination mapper is actually composition, so it just extracts the type from the event and then looks it up into this map here. Very simple, very basic. Honestly, in practice, that's mostly how my mappers work. But again, your mileage may vary. It could be that you have more complicated situation. It's flexible. You can do it any way you want. Now let's connect to that broker. There we go. We have indeed a context here. It contains the state, contains the configuration. That's all internal stuff. You don't need to worry about that. And now let's post that event and see what happens. It returns the event, but I did not see this printout. So why not? is because I have not added the listener yet. The previous example, the listener was already added. Now I have not done that yet, so let's do it here. So the listener will register this router in that broker. There we have it, and it indeed, let's capture it. Yeah, the listeners itself are structures. In this case, it even has unique ID. That's all internal stuff. In case you want to unregister that, it knows which. So in the background, in this state here, this object, it even contains the consumers and stuff. All the internal JMS stuff here is encapsulated in that state. I'm using a type, an object, instead of a record because listeners refer to the broker, which refer to the listener, and you get a reference loop. So if you ever would print it out, you will get a Stack Overflow. So that's why it's in a type that hides its context when printing. Now we have this listener. Let's post the event again, and now we see the expected results. Now we see that it's printed out. So the message is indeed posted to the london.clojurians.in topic, and it's received back by the listeners and passed on to that handler. We could add another listener, because what this handler does here is create a new message, event evt/out, but that again is just lost. We assume that it's posted to another topic, but nobody's listening to it. So let's add a listener there. I'm adding a very simple listener. This is an example of how you do not need. What did I do? That's true. Did I make a mistake somewhere? Okay, yeah. What I omitted here was the destination. Of course, I need to tell the thing where to listen on. That's the one. Now it's good. So it says, hey, you're not telling me where to listen, and that's what the exception is about. Now we have a second listener, and now again, let's repost that event. And now we see not only that the original event is handled, but the resulting event is also printed out here, as we see. So now it's also processed. And for the sake of example, let's unregister it again. DL2 it returns true. If I call it again, it returns false because it has already been unregistered. Now let's post it again, and now we see that it is not called again. So the listener is actually, the consumer is actually has actually been shut down. So yeah, that's I think it's enough for the code, and I think also that I'm a little bit past my time. So yeah, thanks for the attention. If there is, this is the list of links that I promised earlier. So if there are any questions regarding this, go ahead.